Yeah, so my name's William Becker. I'm the training coordinator for machine learning at ECMWF. And I wanted to welcome you to this series of webinars on the ECMWF and member states Anemoi framework. So we call it Discover Anemoi. It's the first of a 6-part webinar series. So as you can see in the right of the slide, we have the introductory webinar today with Jesper. And then we have another 5 webinars covering from datasets and graphs through training, inference, and the last one, which is on aimed at developers. All of the webinars will start at this time, so that's 3 o'clock Central European time, or 2 o'clock in the UK, UTC. And the QR code below is where you can register for those webinars. You've probably already been there if you're at this webinar. There's also the link there in case you need it. And before we get started, I just wanted to tell you that there will be time for questions at the end. So we will have maybe around 40 minutes of presentation, plus you can leave questions in the chat, or you can raise your hand at the end of the webinar and come on the camera. And also to point out that the webinar will be recorded, and we will make the recordings available after the webinar, and we'll send you an email with those. So I think without any other comments, I will hand you over to the presenter, Jesper Dramsch, who will introduce Anemoi. Over to you, Jesper.
Thank you, Will. Hello, everyone. I hear that people are still joining, but we'll just go ahead now. So this introduction to Anemoi is basically the idea that we'll get an overview of the in-depth talks we'll see over the coming weeks. So Anemoi has grown to become a whole ecosystem that I'll introduce, and I'll give you a high-level overview of the different components or the core components within Anemoi, and then you'll be much more prepared for what's to come within the next week, and you know how datasets fits into the grander structure or how to develop things in the end. Anemoi itself has a couple of goals. It's to develop an open source framework, essentially. So it's open to anyone. You can download it right now, run with it right now. And it's for data-driven weather forecasts, or AI weather forecasts, as some people call it, and to running those in operations, which is, of course, an extremely important point, for example, us, but also for national weather services, and to run these robustly and with high resilience. And we work on this in collaboration with the center's member states and other people that have an interest in this. People have contacted me on LinkedIn to work on the documentation and all that, who are not directly member states, but are interested in contributing to this honestly exciting project. And yeah, the really cool part is as well that we have global models in here, which we're most interested in as a global center, but also limited area models where national weather services are more interested in running these from the boundaries that we make available. So Anemoi has already been used by Met Norway and the German Weather Service, which Met Norway have published BRIS, which is their data-driven weather forecasting system, and AICON is the AI version of ICON from the ICON consortium. So there's the German Weather Service and the Swiss, as far as I know. But yeah, as for goals, continue it. It means that we rely on existing tools. We don't want to reinvent the wheel, especially with these large distributed systems that we need for training. We need to rely on tools that have been battle tested by massive open source communities. So you can see right here, we're using PyTorch, we're using Lightning, Hydra, XAR, Xarray, EarthKit, and so many more. We focused on the best use of resources. So how can we optimize the file system? How can we optimize the use of GPUs? And basically, how can we balance all this? Because if you've done machine learning training before, you know that essentially there's always a bottleneck somewhere. If you have these massive models, it means your bottleneck is usually process communication between GPUs. If you have massive data, it means your I/O is a bottleneck, and we're trying to really address it at all of these intersections and piece by piece optimize how we can do massive training over distributed infrastructure on models that don't fit into a single system. And we want to make R2O, so this is research to operations. You might hear a little bit more about this later on, as simple as possible. So essentially, we want Anemoi and the models that are built using Anemoi to fit into your existing ecosystems. So that means meteorological evaluations should be as easy as possible. We do these, for example, by writing out files if you want to as grib. If you already have your tools that use grib, then you can literally just take that forecast and pass it into your standard evaluation and diagnostics tool chain. And the delivery of code and weights to production. So how do we make our model itself as small as possible and as fast as possible to load without having to have specialized machine learning knowledge? And this can be really tricky because people build all of these different models. So there's a lot of work going into all of these goals, essentially. As for the user base and how I think about it, we have 3 different kinds of users for Anemoi. And you hopefully see yourself in at least one of these. Maybe there's also project managers, but we'll keep those outside for now. So first of all, we have the researchers. These are people that would more modify configs, do experimentation, and do improvements of specific models. So try to basically use the existing software in a way to train and build these models and see if they can build better data-driven forecasting systems. Then we have developers. These are involved in modifying the code base, so implementing new features. For example, we had someone that from MeteoSwiss who was working on basically looking at how to replace nans in the data, so non-existing data, because a lot of the pressure levels don't exist in the Alps, because they would be right in the middle of the Zugspitze or any of the other peaks. And then, of course, operations, which runs the Anemoi model, and that should be a common interface, and it should be on reliable infrastructure. So when there's a huge power outage in your GPU cluster, it should be really easy to literally just port it to a different space, and from there run the model without any delays in your expected output. So resilience, reliability are at the core of this this approach to make it, first of all, that, but also make it reproducible. We know that with machine learning models, we have a lot of stochasticity, which is not an easy word for me, sorry. That's where my lisp is coming out again. So that's where a lot of randomness is introduced into models, and we want these models to give us the same output if we give it the same input. So working on all of these core issues is really important as we address these 3 user needs. The main components and design decisions around Anemoi you can see on the right here if you see my cursor. Otherwise, I can also do the laser pointer. We have training that interfaces with models and graphs. Inference is parallel to training using models and transforms. And we have datasets, which is also used by training and by transforms. So we see how all of this ecosystem is interconnected. We'll have a deeper look at that in a couple of slides. What this means is we need object-oriented design, and heavy use of factories, so we can instantiate objects from config files so you can switch out components in your training, in your model. We'll have a look at that a little bit later with an actual hands-on example of switching out core parts from our model just by modifying the config. Each component provides one or more command line tools, so training doesn't have to run in Python. You can literally go anemoi-training, train, and it will start training a model for you as long as the configs are set up correctly. Anemoi datasets, same thing. Anemoi datasets create, and it creates a dataset for you as long as the configs are correct. You can see this right here, and then inference is inference run. So we have tried to make this as coherent and cogent as possible. So the use of this is as intuitive as a complicated tool like this can be. So then for R2O, like I mentioned, we want to make it fast. So we minimize the software dependencies. That's why models and training are separated. So there is a magic boundary here where we can do a lot in training, do all these fancy things, visualizations, do map projections. But when we have a model in the end, we don't want to load all that plotting again. So maybe some of you have experience with the Python ecosystem and have used Cartopy before. Well, Cartopy is really, really cool and super useful. It can do all of these projections for you. So if you have your data and it is registered, you can project it into the correct map space. However, if you install it on certain systems, Cartopy is a 2 GB dependency. That is massive, and no one actually wants to run that in operations because you shouldn't be using these projections when you actually do the operations. This should be done before or after. So these kinds of things you really have to think about. And like, I don't hate Cartopy, I'm just very careful of introducing these dependencies right here in models and in inference. Now, yeah, inference training, they're independent. Each component collects metadata that can be used by the others. So what we actually do is once we create a dataset with this command, this dataset has information about itself stored as metadata, as a additional entry in the dataset itself. Anemoi training then takes this and actually propagates it through and also saves the information about itself, so the training itself, and all of the config entries that you have changed and all of the things you've done during training, to give that then to inference and to give inference the information it needs to basically say, all right, I need to run this in a certain way. I know what kind of data set was used to create this. I know what kind of training was done to then build the model around it. And in inference, we can use all of this provenance to actually then run that in inference. And the cool part also is, once we actually go, and 2 years down the line, we have to go back and we're like, we had this amazing model, we don't know anymore. We can go into the model itself. The model itself in the checkpoint knows all of this information to recreate it. Of course, this is idealized. At a certain point, there's always a little bit of non-reproducibility in compute systems, hardware changes, data changes. We have sometimes just catastrophic data loss when a certain day isn't available anymore. But like, we're going to 99% here, and there is the possibility of actually using this and reusing this at a later point. As a matter of fact, we already have an example of this where the current operational or pre-operational AIFS model was ported from the original AIFS code into the Anemoi code. So we were able to do this by using the information that we had gathered during training to actually be able to, to reinitialize this entire model in Anemoi. Now, in the very beginning, how this looked like, this was the first sketch, the idea, all right, we need Anemoi datasets, generate data, read data. We need Anemoi models with a PyTorch model, with different layers in there, with pre-processors and post-processors. And the distribution has to be in here, and the actual model has to be in here. And training then has a forecaster, so we know how to step through time. And the trainer that handles how all of this is actually passed through to experiment trackers and to logging and all of that. And you can see that training is pretty massive and also has all the configs in here. And then utils is actually used for graph generation and debugging and provenance, the provenance we were just talking about. And in inference, we use the AI models plugin. So this was the initial sketch, essentially. This was the pitch, how we build this. And the next slide, I have to warn you, like it's pretty massive. You don't have to take it all in, but this is the ecosystem now. You can see training right here. And this interfaces with data sets, graphs, and models right here. And then these are passed out to different artifacts that we get, like a model and different logs and all this. And this is then taken by inference, and inference goes in, takes the model, and passes this to AI models. So we can see that the interactions in this ecosystem have grown quite massively. So even if something is outside of a core component, it still has interaction interfaces with these other components. Now, this one I'm literally showing for effect, so you have an idea of how all of these are connected, but it's also more, you know this exists, but you don't have to fully like remember all of this, that, oh yeah, down here there's something coming out of graphs, like a graph file or a grid file. So really, the ecosystem is highly interconnected, and we'll have a look at those components now. It all, or for us in Anemoi, it all starts with a data set. So essentially what happens is when we create a data set and we read it in our Python, we know that we have 4 components. We have the dates, we have the variables, we have the ensembles, should they exist. If you have a deterministic forecast, your ensemble dimension is just a singleton dimension of 1. And then we have the grid points. You can see right here that even in a lat long grid, we are just stretching it into one long component, because that's the beauty of Anemoi. It is using graphs, and the graphs itself can know where each point is in space. So we can pass in this vector of information right here, because let's say point 3, we know point 3 is in Reading, and point 4 is a little bit over in London. So it is this interaction between graphs and making this optimal, so not giving so many dimensions that this doesn't work anymore, but the graph can know all of this information. And then Anemoi datasets makes this informed choice of chunking everything. Currently, the main way to chunk is along dates. So we know, or in the date dimension, this means that when we load our data during training, we know that one chunk contains all our grid points, all our variables, all our ensembles. There are some changes to it already that optimize this as well if you're doing distributed training. But the main thought behind this is that accessing this information and figuring out, oh, where is the date, is a really, really slow process. So instead, if we use this chunking approach, we know we get a chunk, we have a date, and then we can load it. And basically that way, we don't have to know where everything in this file is, and we can access all of these parts in an optimal way and reduce I/O. So this is a very simple file structure, and it minimizes I/O and memory requirements. So yeah, there's actually a second part in here that I don't have on the slide, but all of these data sets also make available the statistics of each each variable. And that means that if we have, for example, rain in here, we know the mean, the standard deviation, min, max from it without having to load all the data and then calculate it on the fly. So all this, what we call in statistics, the population statistics, the descriptive statistics of this data set are metadata, additional metadata of this data set. And this means that when we do normalization, as we have to do in machine learning, we can do this without having to load the entire data set, which is great because some of our data sets are terabytes, and even our supercomputer does not fully hold a terabyte in RAM to quickly calculate some of the statistics. Now, the goals for Anemoi datasets is ensuring that the data loading is hidden beneath the training costs. So we are never I/O bottlenecked by the disks. Then porting the datasets, like I mentioned, opening the ZARs within the training code and making it super easy for us. So we never have to worry about, oh, did we access our data in the correct way? And it handles merges on the fly. And this is really cool. I have a slide for this in like 1 or 2 slides. Features are we can create these ZARs. So Anemoi datasets is for both the generation and the reading. We get it from mass, from grib, from netcdf. We chunk for speed. It's not for interpretability, very clearly not. And the calculation of the statistics. So all of this, and you can read, all of this is open source, so all of the documentation is also open for everyone to see. If you have more questions about datasets, you can go to anemoi-datasets.readthedocs.io, and this works for all the other components as well. So for training, for models, and all that. So you can see all of this interconnection of your nodes of putting different data in here works that the tools are to build a ZAR file from a list of sources right here. You see, this is the input. These are your sources. So filters then allow for data transformations. So for example, going from wind speed and direction to UV components. This is a very common one. This is one that we do as well. So we have the UV components in here. And you can see that different sources are then aggregated into this data set down here, where we get our ZAR file, essentially. And then we want this to be easily extendable to new sources and new filters. The first step where we were actually doing this was working with Met Norway, who have a slightly different system to Mars. And we were then seeing how can we extend the system that already exists to also take in data from their archival system. And yeah, this is essentially what... sorry, I'm getting distracted by questions, but I think my colleagues are looking at the questions. And we can build these large data sets because it can be done in parallel and it can be done incrementally. So even if your full generation crashes, you have a system session, you can pick it up and then build more onto it. Or literally 2024 is now done, increase your data set by the next year. And this is also a nice part about the chunking, that we can literally just glue on another piece and work with this. Then about the usage, this is where we talk about merging and all this. So when used, datasets can be lazily, which is important, combined into virtual datasets. So you can see right here, it may be a little bit small. I hope it's okay for you. You can see we have 2T, MSL, and SP. And right here, we have 10U and 10V. So wind components and like temperature. And these have the same dates, so we can join them into one dataset. And we literally just do this by giving open datasets a certain request. So we go to the one dataset that has 2T, for example, and one dataset that has 10U and 10V, so UV components. And we just tell it, all right, those are the two. So get me that virtual data set and give me that for training. We can also concatenate if there's more, like the historical data in this data set and then modern data in this data set. We can just point it to those two and basically say, all right, give me the aggregate out of this. And there are many other ways that you can merge and replace, sort, select, drop data with these kinds of requests that you can then also use in Anemoi training actually to build these data sets from the config file without ever having to change your your loading. And wait, there we go. Yeah, so this is allowing you to then also try out new variables. So you have basically you build your standard data set with the standard variables that you want. Maybe it's an error 5 data set or something like that. And then you can just tack on new variables and do experimentation that way. So you can find out if you can do snow, you can find out if you can do different pressure levels. And all of this literally works in this super flexible way. As long as you have the data set somewhere and the dates match, or you can concatenate them in a certain way, then you will be able to train with this. Now to Anemoi training, because Anemoi training interfaces directly through this open data sets right here. And Anemoi training itself is the code to train models. The core components here are Torch Lightning, which is basically sitting on top of PyTorch and is taking a lot of the complicated machine learning stuff away from the user and even the programmers. So we don't have to implement everything from scratch. And Hydra. Hydra is essential for configs. So we have over 300 config entries in our training config that you can switch, you can give new entries, you can literally play around with it. And Hydra is making all of this very, very, very easy. You can either change the files or you can even do it on the command line. And the way that we've written Anemoi training is even if you change it on the command line, in the end, we know what you actually did to train this model. So none of this information is ever lost if you're using Anemoi training as it's intended. Now this has stopped working as well. There we go. So some of the core features, core points of Anemoi training is we have multi-node and multi-GPU training support. So you can literally run this on GPU clusters in the cloud. If you have AWS budget or any of the other cloud providers, you can spin up your instances and you can train across those. It's deterministic training with probabilistic training coming soon. So we are currently in the process of getting probabilistic scores and all the infrastructure to run probabilistic training in shape to also release. Then callbacks for all the things that you want. For profiling, so how fast is your code and what is not working, evaluating, for plotting, and for logging intermediate results. I have a slide for that in a couple of slides where we have an example of the experiment logger MLflow, where all of your training is actually logged and you can always go back and you can even compare different trainings. Like I mentioned in the very beginning, we try to reuse components that already exist that have been battle tested. So then implement various losses that you can literally switch out in the config as well. And you can easily write your own loss for this as well. So if right now you're looking at something and you're like, let's say we're a couple of months in the future and you're training your probabilistic model, and instead of CRPS, you want to run the SEEP score on rain, then you can implement that easily if it's not already in Anemoi. So this extensibility is very, very important in the design decisions that we've taken for Anemoi. This is the tracker, the experiment tracker that I mentioned. We interface directly with MLflow, but we have switched from using weights and biases before to using MLflow. So all of these are either implementable or have already been implemented. And this is really, really important. I think everyone that does machine learning for a little while is at some point looking back and wondering, how can I find the training curves for that kind of experiment? That was the good experiment, and now I have no information how it actually happened. So tracking all of this is essential. So setting up MLflow and an MLflow server is usually a really, really important step in doing research and doing this kind of model development. Then, like I mentioned, Hydra for being highly configurable, and interfaces directly with Anemoi datasets through the open datasets command, and Anemoi models through the Hydra configuration. So it then goes down and basically instantiates the Anemoi model with the kind of components that you are requesting. And then Anemoi inference is using the metadata that we store in the checkpoints. Here we see how we can actually switch out these components and how Hydra is making this really, really easy as well. You don't have to care too much about the exact details in here, but we have a GNN on the left, a graph transformer in the middle, and a transformer on the right. Those are all pre-written configs that we already ship with Anemoi training. So what you can do is Anemoi-training train, and then just switch out the model for a GNN for the graph transformer or the transformer over here. And you can see that these sometimes even have different config entries, but in the way that we've written this with a lot of care, we have made this so it's easily switchable, even if not all of your config entries are overlapping. So you can see right here, a transformer that classically has a number of heads is right here. We marked it as transformer only, whereas right here in the GNN, you don't see this. The graph transformer also has it. So you can switch these out on the command line, and then in inference, we still know how your model was trained, because all of this information goes straight into our metadata that is saved. So easy, reproducible, and it is also easy to extend with new models and components, because you can see right here, processor target. It targets the Anemoi models layer processor transformer processor. So right here, if you were to write your own fancy processor, you can switch that out super easily by writing your own and then just instantiating it here. So you don't have to re-implement all the pipelines that are in Anemoi training, but all of this actually exists in a way that you can say, all right, I want to try this different kind of thing. And you don't have to use anything out of Anemoi models itself. You can replace it with something that you came up with. Now, just one example. Currently, AIFS, as it runs, is having this graph as the encoder. This then goes down to the transformer processor. We can see that this is going along bands that spiral around the Earth. And then there's a decoder right here that goes back and out into a graph. So we have graph, encoder, transformer processor, graph decoder, and you can already imagine that this is literally just this switch of a config to get this kind of training out of Anemoi training. The MLflow then looks something like this. MLflow is standard software. You can set up a server locally, or you can even have one in your organization. And then the tracking literally looks like this. So if we're comparing two runs from one experiment, then we can see that the validation of T at pressure level 100 with different scalings right here has a better curve, a better validation curve in orange, and the blue curve is a higher loss. So we probably want to go with this kind of experiment. So you not only have the information, you can also make decisions based on that information, which is me literally just selling MLflow. We haven't written this. We have only implemented the interface to it. Anemoi models itself sits underneath the training. So these are building blocks, as you've seen before, to implement the data-driven forecasting systems. We have models, we have blocks like the encoder, decoder, processors, and we have layers in there. So those are the transformer layers, the GNN layers, and different attentions and all that stuff. Design choice is it's graph-based or similar outer layers. So basically what is happening is we know the world is 3D, and one of the easiest, in parentheses, ways to deal with this is with having a graph that already defines your connectivity around the world. So right now, Anemoi is graphs, because this is a very natural choice. Once you understand graphs, or you can use them without understanding them because we've written the software for you, then you can run these in a very organic way without having to do all of these pre-processing steps of going, for example, to the cubed Earth or all these other projections that all have their own problems, because we know any projection from a 3D sphere to a plane is going to come with trade-offs. This provides high levels of flexibility on the input and output data. We literally just have to say, all right, we have this data, it should be somewhere here. If you define the graph, then you can run it. The inner layers can be either attention or graph-based, like I mentioned, and you have multi-node and multi-GPUs to scale the large models. So we can actually take a model, split up the graph, and shard that graph over different GPUs, which is, like, I'm sorry to say it this way, but to me, this is mind-blowing. Like, being able to automatically say, all right, my model is too big for one GPU, so now just increase the number of GPUs per model, which is one config entry. Then our software, so Anemoi training, basically figures out how to shard the graph and which graph goes where on the GPUs. Yeah, so one-hop graph, head sharding, all that stuff. So it works for GNNs, it works for transformers. And basically, this ensures that your model design, doing fancy, really high-resolution graphs, is not limited by GPU memory. And yeah, people have already benefited from this because our global model is great. I'm very proud of the work that we've done. But whenever I talk to people that work in LAMs, and I'm sure like at least half of you in the audience do, you're like, so yeah, my data has 1 million points at minimum. What do we do? And so you want to be able to shard that easily, because this doesn't, you can't compress it onto a GPU. At some point, you have to push it out to multiple GPUs. And yeah, we have these cool like GraphCast style, Oscarson style, and AFS models that are supported by Anemoi. Yeah, further models can be easily created. We've seen this with AICon, we've seen this with Breeze. And when I say easily, it's always easily. It's tough learning new software. That's why we do this webinar series. And we want to onboard you as pain-free as possible, which means we're doing several multi-hour webinars. Anemoi Graphs itself is really cool because it's also highly configurable. We have all of these different graph generation ways. It's integrated with the Anemoi ecosystem. It includes graph inspection tools, so you can look at your graphs and see if these are working correctly and if the setup is correct. And it's optimized for GPU. So even if you have to do certain things, this is going to be a PyTorch object in the end that can be loaded very easily into GPU storage. Then you can see right here, this is a global grid. This is basically the AFS grid, where you see the blue ones are the processors and the black ones are the dots of the actual input data. We have limited area modeling, which if you think about just this one would be a limited area model, but technically this is a stretch grid. So we have a global model as background, and we have a cutout in here that is connected with, which is the beauty of graphs, right? I remember back in numerical methods, doing the work of doing like a flexible grid is insane work, right? Entire PhD theses are involved in making this possible, from going from one cell size to another cell size. How do you define the boundaries? The beauty of graphs is you literally just define the connectivity, find the neighborhoods, and then you can have this cutout of this fine scale model in this coarser scale model that is your global model. And we also support hierarchical graphs, which is especially important for AICon. Dynamic graphs are in process, and I think I need to speed up because I was like, oh, I don't even know if I can fill 40 minutes, and now we maybe halfway through. So I'll keep the pace a bit. What comes next? Hierarchical graphs fully, and then multiple decoders, multiple encoders, which is tricky because it has to happen on the model level. So we have to figure out the communication, but also on the graph level. So how does the communication between different encoders with different input structures and output structures actually work? Anemoi inference itself, I was already talking about. It basically takes the metadata and then it runs the model. So what's happening here is we have our trained model in inference mode. We do the discovery of those model parameters from the metadata. This means we have a list of prognostic, diagnostic, and forcing variables. This is one that I'm really proud of because I worked on this. So in normal machine learning, usually you have one input, one output. But we have written Anemoi models and Anemoi training in a way that it can actually, you can use the config to switch out variables to only make them diagnostic. So what we do in AFS, for example, we have a lot of forcings. That is, for example, the time of day and the solar radiation. And that is data that we only want to go into the model. It should only inform the forecast state, but we don't want to actually optimize for it. So we don't want it as an output. We have prognostic variables that go in, that go out. And then I know some people might cry at this because, like I just said, we're using the same vocabulary as weather people, but the diagnostic variables are still optimized for. So when we train a model, we are still optimizing against those diagnostic variables. So they're technically not diagnostic, but they are variables that are magically falling out of the model without ever having been in the input data. So in our training, we know this, but in inference, we also need to know this. What kind of data is in our input state? And what kind of data is in our output state that needs to be saved, but that doesn't go into the next step? Because usually how we do data-driven weather forecasting is we take a 6-hour step, and then we take a 6-hour step, and then we take a 6-hour step. So it always auto-regressively feeds the data back into itself. And when we have this three-pronged data, where some of it is only input, some of it is input and output, and some of it is only output, then we have to do this fancy handling of the entire thing where we know, all right, the diagnostic data over here, which one is it? This one. The red one over here is actually going into the results, but it is not going into the next input tensor. So right here, you can see it. It's a really nice graphic. I should be using it much more. But essentially, yeah, we have the constant forcings. We have the computed forcings. We have our inputs. And from our inputs, there's part that is one of those three. So that's how we step through time. And yeah, then we provide full control of input and output to the users. So what you can do is use an output of a physics-based NWP analysis or ensembles or anything else as initial conditions. What we've done is we train on error 5 first or something like a reanalysis data set, and then you can fine-tune on a forecast data set, right? So you basically shift your distributions that the model knows slightly towards what actually runs in operations. And that's how you can then run that in inference. And in progress right now. Also, we're looking at allowing coupling of 2 or more data-driven forecasts. This is very much like bleeding edge, not even leading edge, where we can train an ocean model and an atmosphere model and run those in parallel and have them communicate. Because especially the problem with ocean and atmosphere models is the ocean is much slower. So usually you want to have a forecast that is 24 hours. So how do you actually have these communicate with each other when this only generates an output every 4 steps of this forecast? And all of that handling is something that is on like very high on the roadmap of making this work. Then we have Anemoi Registry. I'll speed up a little bit, where all of this is then saved. You can look up the data sets, you can look up your experiments, and all of this tracking is really nice visualized. So you can see right here that this experiment, the solid setter, with those outputs right here, the experiment outputs, has been generated from this experiment and these additional data sets. So this was pre-training, this was fine-tuning, and this is the evaluation that you can see actually also right here. All of this tracking of the metadata makes it possible so we have full provenance of our experiments. So when you look at II4V, you know this went through this kind of training, and you can click through, oh, what is actually an AFSEAAN, blah, da, 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 da. And you can then see all the variables where you can actually find it on disk and all of these things. So really making it nice for the user as well to go back and be like, what did I actually do here? Why did this work? And how can I recreate it? So code to manage the catalog, training data sets, model configuration, weights, evaluations, and with a strong emphasis on recording the lineage. Collaboration is at the core of this. You've seen this. We're putting this open source. We're putting a lot of developer time behind this. It means that all code reviews are via pull requests, even internal ones. So just this morning, I had a message about one of my pull requests, and I had a message asking about a different pull request. So it is really very level playing ground here. The only thing is sometimes as an admin, I have to go in and fix CIs, and then it has to be very quick. So it may bypass a pull request in very special circumstances, but that is very, very, very rare. We use pre-commit checks to ensure code quality. So if you're very new to Python development, you literally just install this, and it basically checks your code once you commit it and says, okay, this code is it should be written in a different style, so I'm fixing the style for you if you want to. And this has saved me a couple of times, even when I forgot a print statement somewhere. I'm one of the family that does the print here when you can't figure out why something is broken, and it will tell you where your debug statement and your actual debug statements still are before you actually commit and put it into a pull request. So it saves me from looking a bit silly sometimes. Then GitHub Actions run all of this automatically as well. So the GitHub Actions then can automatically fix some code and enforce some of these limits. And we have CI/CD set up. So all of this, when we do a release, can be pushed to PyPI. So you can literally pip install Anemoi training, pip install Anemoi datasets. Anyone can contribute. Like I said, it's fairly equal playing ground, especially after you've done the entire webinar series. I'm sure it'll be much easier to understand like the whole ecosystem, because it can be quite overwhelming in the beginning. What does Anemoi enable? And this is where we're in the fun parts. We see right here, we have building coupled Earth systems. Oh, this should be running as well. Sorry. There we go. So we can see, is this ice? This should be ice, I think. And this is clouds. So new kind of atmospheric fields that aren't in Era 5, that aren't in the classical data-driven forecasting models. Then we can see this deterministic and ensemble model. So no, well, I think this one is one of our diffusion models, but you can see how these progress through time. Over here, you can see the work of Met Norway, which was the stretched grid that we saw from the beginning. So coarse global, and then very fine over the Scandinavian peninsula right here. So you can see really cool how this wind is coming in and then is hitting the shore. We all know the beautiful fjords right here that are very, very well at deflecting wind and all those shenanigans. And of course, running all of these models. So currently we were on AIFS pre-operational, and we are working on the operationalization of AIFS in 2025. This is on the annual plan. This will be happening, which is terrifying, but also fantastic. And all of this is on charts, open for you to explore with a common interface using the infrastructures that we already have in place. So it's collaboration without aggregation around a single model. That's why we have all those windmills. Get your name on here, build a really cool model, beat ours, beat all the others. And please share the config after, because we really want to know that as well. And yeah, what's coming is ensembles. So you can see right here, this is the IFS ensemble against the AFS diffusion. Then dynamic graphs, what happens if you have observations? You need dynamic graphs. So these red ones are observation data that is included in the training, which is really, 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 really cool work. And then Earth system components. So you can see the mean wave here. This is work by Sarah. This is just also really cool to see. So this is comparing IFS against ERA 5 without waves in blue and ERA 5 in with waves in red, in green. And this is one of my favorite visualizations out of Anemoi. So yeah, you can really see that there is a lot of fun things to come. This is just a list. Inference is also becoming parallel, just as a note. And yeah, with that, thank you so much already for your attention. This was a lot, but I hope this gives you an overview how the different components from this ecosystem interact and how you can already get a bit of an idea what is to come in the next couple of weeks.
Great, thanks, Jesper. Fantastic. I can see that we've had a lot of questions in the chat. So now we do have a few minutes left. If Jesper will answer some of the questions. I see a lot have been answered by Baldwin and others who have been tirelessly working in that area. There might be a couple that I saw. I'm not sure if they have been fully answered. I think there was one on. Can you see the chat as well, Jesper?
Yes.
Okay, so God, lost it now. I think there was one about whether so someone's asked, is orography and topography used as an input, or is that something the model learns implicitly?
Depends what you want. So for AIFS, we are not using it directly. We're using the standard deviation of the orography, which is basically also accounting for subgrid effects of the orography. Because if we have a model that is at 096, which is around 30 kilometers, I think, maybe, that means we're missing a lot of the really, really high variability topography and orography. So it could be a literal variable, but oftentimes it does learn some of it by itself. I've seen a really, really interesting one where we have like trainable parameters and you can visualize them. And I've seen one trainable parameter that apparently has been explicitly learned for Lake Victoria, because it's just such a large body of water that influences the climate in Africa. So it's your choice. The dataset can be generated, and you can see if adding in orography, topography, or subgrid representations thereof will improve the model.
Okay, I've got one one more question here that I don't think has been answered, or it's probably been touched on. Will deterministic and ensemble IFS disappear when AIFS kicks in operationally? If so, how do you provide new training data?
I don't think that's a question for me. That's a question about 3 levels above me, the director level. I don't think so, personally, because I mean, we haven't even run out AIFS for that long. It's been running for a year now. We need to know it's stable. We need to know it can run, and we have a changing climate. So when I'm being funny, I'm always saying IFS is our data generator. Of course, it's much more because we're also learning much more physics. But if AIFS runs operationally, there is, of course, then also space to extend IFS to higher resolutions, because machine learning is very tricky. If you don't have high resolution training data, you cannot get a high resolution machine learning model. So it's always limited by what we actually have from physical models. I don't think in my career, which hopefully is still a couple of days, then it will stick around.
Okay, I think there's one more that I might pick out, and then, well, it's nearly the end of the hour, and I think possibly if anyone wants to ask like 1 or 2 more questions in the chat, we can possibly deal with 1 or 2 more. But the last one that I've got here is, do LAM models need to be put in a global scenario as Met Norway did?
No, that's specifically why some people prefer a LAM model. You need the boundary, so you still need boundary conditions that you need to get from somewhere, and I think it's an ECMWF product as well, to get specific boundaries as the initial conditions, but then they don't have to be run in a global context. However, there is a question of why do it if you can like actually generate this. But one thing, I don't know if everyone's familiar with like data-driven weather forecasts, but running one of these literally takes a minute. So if you can run a global model in a minute suddenly, the question is, why wouldn't you? But that is, of course, a very long discussion, and I'm poking the hornet's nest a little bit. I'm aware of that, but this LAM is a proper local area model.
Okay, there's also a question about computing. So what's the minimum GPU plus CPU config to run any of this? If you can answer that.
I'm being a proper scientist here when I say it depends. So we are training on A100s with 40 gigabytes of RAM. Technically, if you either have more GPUs that are smaller, or you literally just build a smaller data set, you should be able to run this on smaller data sets. But it is basically a trade-off between what you can fit in a GPU and the resolution of your model. So we are currently looking at high resolution models for global, and that means we are seeing where is the trade-off, how much do we have to shard. But if you literally only have a NVIDIA GeForce like a 580 or something with 16 or 24 gigabytes of RAM, or you're going even lower, one of the older ones, and you have like 12, then you have to build a more coarse model, essentially, because that basically scales how big your model has to be. And I don't know what kind of resolution you would need to fit in a 12 gigabyte model, but I assume it's quite coarse, unfortunately, like probably 100-kilometer model, something like that. I'd be interesting to know if you want to experiment with it.
Okay, I think there's one more question that maybe we can do, and then I think we might have to close. So the question is, you mentioned learnable parameters I think, when you gave Lake Victoria as an example.
Mhm.
Do you use additional input maps that you let the mode I learn the content for, or how does that work? I'm not sure if I understood that actually. Does that make sense, Jesper? It's like 3 questions up. 4.
Oh, so basically, we don't give it a map. We give it a land sea mask, for example. That can influence this. But as for the learnable parameters, that is just a free parameter in the model that can learn whatever is useful for generating a better forecast. And it's actually just a side thing of the model. Like most of the core components of the model are other stuff. And that accidentally learned like Lake Victoria. And that is just me looking at those after the fact and wondering why I have this mostly green field with a couple of very, very, very light spots in there. And I was like, wait, overlay this on a map. And then on the map, I saw, oh, this is a spot that is right over Lake Victoria. That is really curious and very interesting. So that was just diagnostics. So going in and seeing, oh, why is it this way? Not me saying, learn Lake Victoria especially well. I hope that answers the question. I also only half understood it, I think.
Okay, I think we're going to have to leave it there. But thanks very, very much to Jesper and also the other colleagues who've been working in the chat to answer all the questions. And thanks to everyone that's come along to listen to it, of course. I just wanted to say one very quick thing before everyone goes. Of course, we have another 5 webinars coming up, so please go to the website and check the dates for those and register if you want to listen. And the other thing is there's a very, very, very short survey. If you follow this QR code here, and we'll also circulate the link afterwards. It's just 2 questions about the webinar where if you want to leave any feedback or suggestions for future training, you can do that there. And we also have our training email. If you have some more general comments that you'd like to make, we'd be happy to hear about those. So thanks again to everyone, and we will close the webinar now. Thank you.